All right, welcome back. Today I'm going to be completing part C of Separations Homework 2. And to do this, we're going to go ahead and continue from our previous part B file we have here. As what we're going to be doing today is we're going to find our bubble pressure, dew pressure, bubble temperature, and dew temperature using our NRTL activity coefficient model. And to do this, we're going to utilize Raoult's law. So we know that our YIP is going to equal our XI gamma I PI set. We're going to be able to use Raoult's law there to first find the most trivial of these are bubble pressure. So getting started here, we're going to set up our components first. So we know we have an isopropanol water system. And since we used P for our props up here, we're going to go ahead and use R this time. So we're going to say that our R is going to equal props. And we're going to do isopropanol and water. Going on from there, we're going to set up our feed compositions. So we know that our Z is going to be an array with 0.3 for our isopropanol and 0.7 for our water. Those are our feed compositions for the mixture that's going to be coming into our eventual VLE plot. So moving on from there, we can go ahead and find our bubble pressure. So we're going to define bubble P at bubble P NRTL this time around. And that's going to be a function of our liquid composition and our temperature. And first things first here, we need to implement our Raoult's law that we calculated, or we've set up here into our function here. So we know that our YP, our Y times RP, is going to be equal to our X times our NRTL gamma, or R dot NRTL gamma. Turn the fans on my laptop. It's getting real hot. I get behind a little bit. And then we're going to multiply that by R dot PVAP at our temperature. And we're going to need that gamma at R, provided X and temperature. That'll give us our YP that we're going to need. And then, of course, to find our P, we're just going to take the sum of all of our IPs. So we're going to say that P equals NP dot sum YP. And then going on from there, we're going to return our pressure, our bubble pressure, and our YP over P, which is our vapor composition. And to check that this is all working right, I'm just going to do a real quick calculation here. So we're going to do our bubble P NRTL at Z, and we'll say 350, as that's the problem we're going to come up upon later for our constant temperature binary VLE. So let's go ahead and check this, see how this looks. Hold on. Oh, I capitalized our gamma here. Fantastic. Those numbers seem pretty reasonable to me. So I think we're good to go ahead and move on to our dew pressure, which will be a little bit more complicated, but not crazy complicated. So we're going to define our dew P NRTL yet again as a function of x and t. I should say y and t. Then for this, we're going to need a niter equals 100, a counting variable, and then we're going to need a tolerance for our later calculations. So we're going to say our all is going to equal 1 e minus 6. Fantastic. Moving on from here, before we get into our if loop, we're going to need to find our vapor pressure at our provided temperature. So we're going to say that PVAP is going to equal R dot PVAP at T. That's all good. And then we're going to go ahead and create an array of ones for our gamma. So we're going to say that G is going to equal NP dot ones like our Y that we're putting in there. And that's just going to create that array so that as we go into our if loop, we can go ahead and update those values to whatever the actual gamma values are. We're just initializing that array, I should say. So now we're good to go ahead and start our loop. So we're going to say for I in range niter, we are going to say that our P old, go here, P old is going to equal 1 over NP dot sum Y over our gamma times our saturation vapor pressure. So we're going to say G times PVAP. Moving on from there, we're going to update that based on our change. So we're going to say our X is going to be our Y times our old pressure all over, looking at the equation here, G times our gamma times our saturation vapor pressure. And we're going to update our X, saying X is going to equal X over P dot sum of X. So now we can go ahead and create our actual gamma value. So we're going to say update our G, because our P old is based off of our G for an array of ones. So we're going to update that to its actual values. We're going to say that G is going to equal R dot N, NRTL underscore gamma lowercase at our X, our T. And now we can make our P new based off of our actual gamma. So the purpose of the P old was to eventually make it so that if our P old was, I think, greater than or less than our P new, it would go ahead and break the function as we would have added up to the 1. So we're going to say that P new is going to be the exact same thing, just with our new gamma. So we'll go ahead and copy and paste that. So now we're going to put in our if so that we'll break out of this loop if we need to. So we're going to say if P new minus P old over P new is less than our tolerance, we are going to break out of here. Perfect. And now that we have this loop, we're going to update our X values. So we're going to just copy and paste this with our P new instead of our P old, same as we did with the gamma. So we're going to say P new. Fantastic. And then we're going to return our P new, which is, of course, our dew pressure based off of the NRTL calculation. So we're going to return P new, X, and I to see how many iterations it went through before we finally found the actual values we're looking for. So to check and make sure this worked, We are going to do the same thing. We're going to check our do P and RTL at Z and 350 Kelvin. Alrighty. Now I put 2 equal signs here for some reason. Shift enter. Fantastic. Those seem like reasonable values to me. So I think we can go ahead and move on. All right, now we're going to go ahead and create our plot for our dew and bubble P's for the given problem ahead. We're gonna create that VLE diagram. So to get started with that, we need to plug in our temperature that's provided, which is our 350 Kelvin, of course. And then create our X1s, our liquid composition of our more volatile components. So to do that, we're going to say x1s equals mp dot linspace. We're going to go from 0 to 1 with 101 points in between. And then we'll create an empty array for our y1s and our bubble p's. And we will update those coming up here soon. And to do that, we are going to say for x's and x1s, we are going to, or should say x1 and x1s, we are going to say that our pressure and our vapor composition, an array, y1s is going to equal bubble p. I think this is correct, actually. That it is. Bubble p nRTL mp dot array going from x1 to 1 minus x1 t. And then we can update that bubble p array using bubble p's dot append with the p's that we calculate above. And then we can also append our y1s with the y1s found up above. Y1s. Fantastic. And then we've got our loop. We can go ahead and create our array. So we can say that bubble p's is going to equal mp dot array of our bubble p's. Bubble p's. And same with our y1s. Fantastic. Now I think we're good to go ahead and make our plot. So to do that, shift enter. Hold on. I think I see. We got said y1s up here. It's only the y1 variable that we're iterating on. So shift enter. Fingers crossed. Interesting. It's taking a little while to execute, so while that's doing that, we're going to go ahead and start to create the framework to make our subplot. We'll need this to execute before we can actually make our plot. So we'll say our figure, as always, is going to equal make subplots. And then I'm going to do a cut real quick just to make sure everything is all right with this taking a minute to execute. All right, after much deliberation and letting the code run forever, I figured out my issue was that I was appending my y1s with themselves. And for some reason, instead of kicking out an error for that, it just was letting the code run and run and run and run. So got a little assist from the AI there, but now that we figured that out, we got this to execute fine. We can actually create our plot now. So, as I said before, we've got our fig equals make subplots. And then, of course, we're going to do our fig.add scatter. We're going to have our x equal our x1s. Our y going to equal our bubble p's, of course. And our name is going to be our bubble, of course, as this is going to be our plot for our bubble pressures. And then we can do fig.add scatter. Going to do x equals y1s. Y, again, is going to equal bubble p's. And our name is going to be dew pressures. Fantastic. And look at that. Fantastic. So now that we've got this plot, we need to go ahead and make our plot for our bubble and dew temperatures. And from there, we can compare the plots that we're generating using this NRTL activity coefficient to some plots that Google's got to see how accurate we're getting here. So let's go ahead and move on to our temperatures. So I'm going to get started here by defining bubble T, and RTL. This time as a function of x and then I'm going to get our initial guess. And as we've discussed previously, a really good initial guess, because for bubble and dew temperatures, of course, as we discussed in previous homework, you need to actually go in there and do like a solve an IV, find the roots for our temperatures, because you can't just analytically solve those problems. So we need to find an initial guess, which a really good initial guess for this is going to be the sum p dot sum of our x times all of the boiling temperatures at our provided pressure. So now that we've got that initial guess, we can define our root function, which, as usual, we're going to call it fruit. That's going to be a function of just our temperature. And then we can go ahead and plug in our equation. So we're going to say that your return p dot sum of x times our gamma values, r dot and RTL underscore gamma x and t times our saturation vapor pressure, so times r dot pvap at RT. And we are going to divide all of this by P and subtract 1. All right, now that we've got our root function, we can go ahead and solve it using our SciPy optimize. So we're going to say that t is going to equal SciPy dot optimize dot root scalar bar f root function with our x naught initial guess equal to t naught, and we're going to do method is going to equal not the Newton because we're going to need an initial guess. We will do the secant method. Dot root. And for this entire big function, we're going to go ahead and, no, not dot root scalar. We're going to go ahead and return our temperature. And then, of course, yep, that function right there, actually, just with r divided by p up here. Enter. All right, that's going to give us our bubble T, but now we need to also find our due T, and that's going to be a little bit more of a complicated endeavor. But let's go ahead and get to it. So we're going to shift enter. All right, so to find our due temperature, we're going to need an initial guess. And for our initial guess, a really easy way to find that would be to pull from maybe part C of homework 1 for separations, where we found our due P and our due T, which I just went ahead and copied over from previous homework, using just our PVAP without the NRTL method. So this is going to be our initial guesses for our due P and our due T that we are going to use to now find our due T using the NRTL method. So let's go ahead and get to that. So we're going to define our due T and our TL as a function of y and p. Then we're going to need our initial values that we were discussing up here. So we're going to say that t naught and x naught are going to equal our due t function up above at r given y p. Then we're going to vectorize this to make everything a little bit easier. So we're going to say VO equal np dot r underscore r t naught and r x naught. Cool. All right, folks, I just realized I got a little bit ahead of myself here. So we are going to do all of this work, this initial guess and everything is going to be for essentially for our part D work primarily. What I'm working on part C, this doesn't quite apply yet. But part D is pretty much integrated into part C. They're essentially the same part in the same document. So I'm going to keep this work here, but just know that this is going to be for our part D that we're going to do later. Well, I'll explain that once we get into our part D. But for our purposes right now, I'm just going to go ahead and continue to find our due temperature using the NRTL method so that we can get our plot together and explain through the rest of part C. So to do that, you need to create a new cell underneath it here. There we go. What we're going to do is we're going to set all of our conditions that we talked about way up here. So we've got for our constant pressure, we are sitting at 1 bar. So I'm going to say P is going to equal to 1E5 pascals. Moving on from there, we're going to set our line space. We're going to say that our x1s are going to equal np dot line space from 0 to 1, 101 points in between. And then, like before, we're going to say our y1s are an empty array for now. And then we're going to say that our bubble t's are also going to be an empty array for now. Now, this will look pretty familiar to our code up here. I'm going to try not to make the same mistake where I had this running infinitely. So we're going to say for x1 in x1s, our t this time and our y1 are going to equal bubble t and RTL by dot array going from x1 to x1 minus x1. And our pressure, same as before. And then, just so I don't make the same mistake, I'm going to go ahead and copy and paste our appends from up here, just changing the variable names. Here we go. Hold on. Copied the wrong thing from my clipboard. Well, for some reason it's not working out. So I'm just going to say bubble t's dot append with RT. And I'm going to do y1s dot append with our y1 values. And then finally, we can go ahead and fix our array. So we're going to set our bubble t's equal to np dot array bubble t's, and our y1s is going to equal np dot array y1s. Fantastic. Please run. Did I make the same mistake? No, I did not. All right. Now we are all good to make our final plot for part C. So to get started with that, I'm going to copy over some of this stuff right here. As we're going to need this half of the plot, I'm not really sure what happened to it here, but in some part of our code it got all kind of wonky, but we're going to make sure to update the layout this time so we can actually see a more representative chart of what we're looking at here. So now that we've got those on there, we can go ahead and use we're going to need 2 columns in 1 row. So let's update the layout a little bit by saying that rows equals 1, calls equals 2. Fantastic. And then updating which this is in. So this is going to be in row equals 1, call equals 1. What am I doing? And then since we're going to have both the bubble and do temperature and pressure, I'm just going to say that these are called bubble and do. And now to add our temperature plot. Update that real quick. We're going to do fig.add scatter. X equals x1s. Y equals y1s. Completely forgot I need to update this to our bubble t's as we're doing our bubble t graphs now. Equals y1s. Row is going to equal 1. Our call is going to equal 2. So this is our second plot. And we're going to say show legend to false, as we already have that the legends being put on there by our first two rows. False. There we go. And then we're going to want to add a 45-degree line on our second plot here so that we can see our azeotropes that we're going to have. So we're going to do big dot add scatter. X equals going from 0 to 1. Y equals going from 0 to 1. And again, we're going to do show legend equals false. And I also need to put in our row equals 1, call equals 2. And finally, we're going to want to update our layout so we don't have something as nasty as our pressures up here, which I'll fix that before we do our final analysis for part C. So I'm going to say fig.update layout. We're going to set our width equal to 800, it's double wide, and our height is going to be equal to 400. Then let's go ahead and show our figure. Beautiful. So as you can see here, we're going to have two azeotropes based off of our XY plot here. And then you can see how our bubble and dew temperature change based off of both the X and Y1 compositions. So now that we have this, I'm going to go ahead and update the layout of our top graph, and then we'll go compare those to some charts on Google. This time, we only want that width to be 400. Interesting. That is not how that's supposed to look. Give me 1 second. Alrighty, folks, I figured it out. It's because up here, when I was trying to figure out why my code was executing for like 5 minutes straight, I changed the amount of iterations in hopes that it would kind of just force the code to work. So I went ahead and fixed that. So you can see here, we've got our bubble and dew pressure graph based off of our X1 compositions and our Y1s. And we have our temperatures. So let's go ahead and go into Google and look up VLE diagram for, we have here isopropanol and water, I believe, from the beginning of the problem. Isopropanol and water. Images. So if we split up into two different charts here. First, looking at our azeotropes, that is pretty much spot on. If you look at our graph down here, we have our two azeotropes in here. Even the colors are kind of similar. That's pretty cool. And then Let's look up our bubble versus dew pressure. Oh, there's our temperature. And again, plot looks just about perfect. So let me see if I can dig around and find this last plot on here. So looking that up, I don't know. I can't seem to find this one on Google, but we've got our bubble and we've got our azeotropes, we've got our dew temperatures, and those are both correct. So I'm going to go ahead and assume that this one is also correct. I think that is the end of part C for homework 2 for separations.